So we are now recording, just to make sure you're aware. And you can see my presentation, right? Hoping. So
Yeah,
this was gonna be tax day, but now we have until July. So Hinsu Kim, I believe, is probably not online, but I was just going to give him an opportunity to present if he just happened to be on. But I know there's connectivity issues, and the other problem is time zone is completely different too. So I was pretty much expecting he wouldn't be available. And then next is Bailey and Jason. Is it you, Bailey, that's presenting, or is it Jason?
No, Jason's going first.
Okay.
Oh, I thought I was presenting next class. I didn't realize that that other group was already almost done.
Yes, it was only the one other person who is back in, I believe, South Korea. So.
Oh, I see.
Yeah.
Okay. Give me a second, and I'll get my presentation ready then.
All right, and let me know. But I think you should be able to start sharing by just clicking on that rectangular box with the arrow pointing up. That should allow you to take over presentation, but let me know if you need me to do something on my end.
All right, is that good? Can you see this?
Yes, I can see it.
And other people as well? I'm just going to assume that's the case. All right, so to start with a quick devotional, I want to talk a little bit about, I'm going to sort of roll into my intro as well with this. I want to talk about the word Ubuntu as sort of the lead into the devotional, because it's a really interesting word. It comes from a couple of different ancient African languages, and it means essentially humanity to others. And the entirety of Ubuntu's mission statement is built around this concept of humanity to others and having free software that's available to everyone. I think that's interesting in a devotional sense, because it's an entirely originally secular concept, but it's still worth sort of analyzing and keeping in mind even from a Christian perspective. I just want to say for the devotional to take note of secular concepts and see how they interact with Christianity instead of just discarding them because they're not directly from Christian texts or speeches. I'm going to open us in a quick word of prayer as well. Dear Lord, we thank you for this day that you've given us, and despite all of the chaos that's going on around us, Lord, we thank you for all of the blessings you've given us. We pray that you keep all of the people who are in danger from this current virus going on, keep them safe, Lord, and keep the people who are dealing with those people safe as well. We pray that you just help the world through this time and bring about what you would want to bring about, Lord. We pray all this in Jesus' name. Amen. So what sets Ubuntu apart from other operating systems? Well, primarily, it's the entire point of it is that it's open to others and available to people who aren't necessarily used to using Linux or other operating systems like that. It is by far one of the most popular operating systems by this point for that very reason. It makes installing the operating system and using it as easy as possible. So in this presentation, I'll be talking about the history a bit, and also some of the different flavors of Ubuntu that are available. They call their different versions flavors. And Bailey, next time, will be talking about the file system and the GUI. Ubuntu was originally founded to take the core bits of stable Debian and improve on them more quickly and package them together into a user-friendly system that is more frequently updated. It was first released in 2004 when Mark Shuttleworth decided that he wanted to create an operating system that was even better than Debian, and has been updating ever since. And like I said, their mission statement talks about humanity to others, and it's often described as reminding us of, I am what I am because of who we all are. And Ubuntu tries to bring that spirit into the world of computers and software. So some of the main flavors of Ubuntu, the official flavors at least, are largely just different desktop versions. So the default desktop that Ubuntu uses now is the GNOME desktop environment, but you can also use Kubuntu or Lubuntu or Budgie or Xubuntu or Mate. All these different flavors are just different desktop environments. Lubuntu is also made to be notably lighter. But then there's also Kylin, which is the official Chinese version of Ubuntu. There's also Ubuntu Server, which is made to handle things like mail, file servers, and being able to host LAMP. And it's also, by default, headless. It doesn't have any desktop environment on it at all. And it's, again, made for servers. There's also Ubuntu Studio, which is for audio, video, and graphic editors, and comes with a lot of powerful open source software for people using it for that purpose. All these different flavors are not necessarily too vastly different from one another, simply because if you really wanted to, you could get base Ubuntu and load all of the packages and unload all of the other load packages from one flavor and unload all the packages that aren't from that flavor and approximately get to the same thing. But the reason that these are separate is because they are optimized for having that, having those things preloaded on them. There's also a number of discontinued official flavors, which are kind of interesting to look at. There's Edubuntu, which was made for education. There's Gobuntu, which was made to have entirely free software on it, but now instead of being a separate flavor, it's just an option in main Ubuntu. There's also Mythbuntu, which was a collaboration with Myth TV, I believe, that tried to make a home media center out of Ubuntu. There's Ubuntu Android, Ubuntu GNOME, which has just been merged into main Ubuntu. There's also Ubuntu JOS, which was made to be extremely efficient for virtual applications and has just been merged into the server. There is Ubuntu Mobile, which was succeeded by Ubuntu Touch, which technically still exists but is not an official flavor anymore. There's Netbook Edition, which has just been merged into the desktop edition. And then there was also Ubuntu TV. These are all a number of different flavors of Linux, and this just goes to demonstrate just how fascinating Linux can be. You can have so many different versions of it that are all a sort of the same operating system, but not really. And I believe that is the end of my part of the presentation. Oh, yes. And then there's unofficial flavors there's unofficial flavors. The most popular, by far, unofficial flavor of Ubuntu is Linux Mint, which was made to look like Windows. And just as Ubuntu is one of, if not the most popular distribution of Linux, Mint is one of, if not the most popular flavor of Ubuntu. There's also Elementary OS, which is made to look like Mac, good for people who are used to that environment. There's Zorin OS, which is specifically made for new Linux users, and it also looks and acts like Windows. There's KDE Neon, which is rather interesting. It's not exactly a flavor, but it's designed for KDE applications to be released on it first for people who are testing and developing those kinds of things. There's also Pop OS, which was made just to have minimal desktop clutter. Linux Lite, which is aimed at Windows users, and it has a different desktop environment. There's also Peppermint OS, which has also a different environment and is, quote, lightning fast. I believe another group actually has Peppermint as their topic. And with that, that should be the end of, yes, that should be all of the different flavors that I was going to talk about. Are there any questions?
So I have one question. So you mentioned the LAMP stack. Can you explain to your fellow students, or do you remember what LAMP stands for?
I believe it is Linux, Apache, MySQL, and PHP. It's a group of applications that are used for making a web server. It's a very, very powerful sort of combination.
Yep, exactly. And some people have replaced PHP with other languages like Python. But
yeah, of course.
PHP is the official P in LAMP.
Yeah.
Or the original P in LAMP. So good. Any other questions?
Have you used other some of these distributions?
My go-to version of Linux is actually Mint. If I'm making myself a Linux like boot stick, I'm gonna put Mint on it.
But you haven't used any of the other ones for certain projects that you've done or anything like that?
I haven't really had to very much, honestly.
Okay.
So I actually personally have used the netbook version, which I guess, according to that presentation, has been merged into the main branch. But that was because of the processor we're using. The processor we were using on this turnkey system. So basically the hardware and software were sold together, was actually using a processor that was commonly used in netbooks. So it was optimized for that processor. So that's why we chose to use that. But then again, support is a little bit more limited now.
Yeah.
Anyone else have any questions? I see a comment from Daniel that Kubuntu is amazing. The KDE Plasma desktop looks so futuristic, so very pleasing look. And then Jessica had mentioned that her dad uses Mint also, so it is a popular distribution for sure.
Mm-hmm.
All right. Well, unless we have other good questions, well, I'm going to go ahead and take over the desktop again. And thank you very much. So, Bailey, I'm guessing you already know that you're next, and made arrangements with your sister to have you speaking in the room. So that's good. And then after that is Mac OS X with Tyler Krautz. And is Tyler here? I have not seen or heard from Tyler in some time. So if you're after Tyler, be prepared to present after Bailey, because I haven't heard from Tyler. And then Ethan is up next with Plan 9 from Bell Labs, which is an interesting operating system. And then Ian is up with Puppy Linux after that. So that's the ordering. And I think we only have a few more left, so we're getting towards the end of the presentations. So again, not too much difference. I might have shuffled some things around. I'm extended some things back a little bit. But Wednesday, April 15th, midnight is Chapter 6, CPU scheduling. My understanding is some of you guys are studying for the quiz on that one. And then Monday, April 20th is the Chapter 8 main memory quiz. And Monday, April 20th is the mass storage one. Chapter 10, May 4th is the extra credit programming. Oh, I'm sorry. The 27th and the 4th, those are programming problems. Both of those are programming problems, not quizzes. And we discussed the page replacement algorithms, and then Chapter 9, virtual memory slide 20 is where we left off. But were there any questions about the problems? I mean, the quizzes or any of the assignments? You're certainly welcome to take the quizzes early if you want to try to get them out of the way so that you don't have to worry about them at the end of the semester. So please take advantage of any free time and knock some of those off. I think that will probably take a little stress off of you. All right, so I don't see any questions, but if you think of one, let me know at the end. Oh, and that place marker was old, but I know where I'm supposed to be presenting. So we were in mass storage, and we talked about the hard disk performance is the two components, main components, are the seek time, which is moving the arm in and out radially along the disk, and the rotational latency. So that's the amount of time that it takes for the information you're trying to get for the disk to spin around underneath the head. So those are the two components. And then we also talked about how the seek time is generally the longer time. Next is solid state disks, and we had a question from one of your fellow students after class. And so solid state disks are becoming more and more popular, primarily because of the speed at which you can read data off of them. It's basically using non-volatile memory, which is memory that does not lose its information when the power is turned off. So you can use it just like a hard drive, and there are many technology variations of that. I talked about how there was a hybrid version with non-volatile memory and conventional magnetic media, but there's different technologies that are being used to try to perform to improve some of the performance characteristics and try to eliminate some of the downsides with solid state disks. So again, remember that it's non-volatile memory, basically. It's not like other conventional mass storage devices, which are magnetic, but it in fact is memory. They can be much more reliable than hard disk in terms of vibration and being jostled around and stuff, and physical shock factor. But the downside is that it can be more expensive per megabyte, and maybe has a shorter life span than magnetic media disks. And in particular, one of the characteristics that has been well known about solid state disks is with magnetic disks, you generally get some indication that things are starting to fail on the drive because you'll get more and more failures, and it'll start acting a little radically. And it sort of tends to give you a warning that a failure is going to happen, so it's not completely a shock. You can see the number of failures, disk components that have disk information that has to be remapped, and how many bad locations are on the disk for magnetic media. But with solid state drives, generally they just fail instantaneously. You have no indication that it's about to fail. It's just gone. So that's one of the characteristics. The other thing is there's some definite problems with it in terms of lifespan. It's basically, for the drive, you get a certain number of read and writes to the non-volatile memory, and then it'll fail. And so typically what will happen is instead of reusing a storage space that was already used, it'll continuously keep trying to use new places in the non-volatile memory for the hard drive, and leave that information, leave information that's on there even if you delete it. So if you delete a file, it is quite typical for that information to still be in the non-volatile memory, even if it's been deleted, so-called deleted from the user. And so that could cause a security issue in that you may believe that you've erased or destroyed information on it, but it could still be there, and it typically will be there. So that's another downside of solid state disk. In general, it has less capacity than its comparably priced magnetic media drives, hard drives, but it is much faster, especially on reading. It's typically asymmetric in that you can read data from it faster than you can write. That is a typical characteristic of it, but it is still much faster than magnetic media drives. The bus can be slow, and especially when connected to directly to PCI, for example, but in comparison to how fast it is because it's memory, but it has no moving parts, so we don't have a seek time or rotational latency delay. It's just like accessing memory that doesn't go away when the power is removed. So I don't know how many of you have seen magnetic tape, but was an early secondary storage medium, evolved from open spools, which is basically a reel-to-reel setup, to cartridges. It's relatively permanent, which means, and it holds large quantities of data. It's very cheap. You can put lots of data on there, and in general, it's lasts a long time. It'll stay in the condition for a long time. Hence, it is typically used for backup of infrequently used data, because backup is great because it lasts for a long time, but it has to be infrequently used because the magnetic tape media has to be mounted and unmounted typically. So access times are slow because you access them linearly, going from start to back in general. And so random access, if you're trying to randomly access a piece of data on a tape, it's 1,000 times slower than a disk. And again, that's why it's frequently used for backup and infrequently used for any other usage. Kept in a spool, sort of physical characteristics. Once data's in the head, the transfer rates are comparable. Oops, sorry. There. Kept in spool. Let's see. Once data's on the head, it transfers about 140 megabytes per second or greater. Typically 200 gigabytes to 1.5 terabytes is a typical storage on a tape, magnetic tape. And it lists a couple of common technologies. Main thing to remember here for magnetic tape, it is a type of storage, mass storage device that is used for backups is the key thing to remember. backups and infrequently used data. So if you have to pull it back frequently, it's less likely used. Disk structure. Disk drives are addressed as a large one-dimensional array of logical blocks, where the logical block is the smallest unit of transfer. That's because of the delays in access times, the latencies of the disk head movement and the rotational latency makes it long. You generally want to read in a fairly large block of data at a time. So the one-dimensional array of logical blocks is mapped into the sectors of the disk sequentially, which corresponds to the different tracks. So sector 0 is the first sector of the first track on the outermost disk. So we're talking about all the way out at the edge of the disk, and the first one, and so on the outermost cylinder, and then as you go around, those will be the different sectors. Mapping proceeds in order through that track, so you just go around that outermost track, and they're all would be sequential. Generally, and we'll discuss, I think it comes up later in a later slide, but you could either store them equidistantly spaced, or more typically, it's based on the radius angle for where it is on the disk, but both of those approaches are used. So the logical and physical address is pretty easy to map, except for the situation of bad sectors. On magnetic media, it's the laying down of the magnetic media is not perfect, and there will be certain sections of the disk that will be unusable because of that. Either the magnetic capabilities of it were not laid down correctly, or over time has gone bad. So you need to be able to map bad sectors. And then here it says in this last one, which I referred to earlier, typically it's a non-constant number of sectors per track, but instead constant angular velocity, which is the angle out. So you'll have a sector at 5 degrees, 10 degrees, 20, something like that, probably smaller degrees than that. But you can see there that as you get closer into the disk, middle of the disk, that the denseness of information stored is greater than that on the outer cylinders, or the outermost part of the disk. So characteristics of using a hard disk from a user's perspective is that you generally have to attach the storage through I/O ports called I/O buses. Typical buses are SCSI, which was very popular, but tended to be a little bit more expensive. Fiber channel is a very high-speed serial architecture, and it can be used in storage area networks. And I actually used a special bus that was used for manufacturing equipment, and they actually use fiber channel, but for the reason of actually reducing the amount of electrical interference, or to eliminate the effect of electrical interference of the actual machines themselves affecting the bus. So that's why fiber channel was used for the manufacturing floor, or is typically used for the manufacturing floor. And then we have I/O directed bus ID, device ID, and logical unit, or LUN, is another one. But these are just sort of examples of what you can see, but is not something that I'm necessarily going to quiz you on. Storage array. So you can have arrays of disks, which is hence a storage array, ports connect to multiple hard disks, and memory controller softwares and VRAM and sometimes NVRAM, etc., is involved with the controlling of the storage disks and buffering and things like that to improve performance. And you can have as thousands of disks attached to the storage array. So you can see that this could be a situation that could be used like for a web server or something like that, where you're expecting lots of transactions and you may be storing lots and lots of data, that you could have a large storage array. And then another popular topic is RAID, which is redundant storage. And so then you have hot spares, you have striping where information is stored on different disks in order to make it more reliable. And so we'll discuss that later in a little bit more detail. So Jacob, speaking of RAID, is there something else?
I had an interview with a company, and they asked me in the instance of adding another server to the current rack that they have available, what RAID method would you use to ensure redundancies and stuff like that? And I told them that I didn't even know what it was.
Right. So we will discuss that in a little bit, but it'll be more extensively covered, I believe, in your text than I actually cover in my lecture. So, and then Daniel interjoked it with a little body we were referencing to a joke for a game. So anyway, so did they fill you in on what kinds of answer they were looking for, or did they just move on? Oh, and so Ochir is going through the different categories of RAID: RAID 0, RAID 1 for speed, redundancy, vice versa. They went at RAID 10. Oh, yeah. Yeah, was a very challenging question, wasn't it? So did you get a job offer at all there, Jacob? And Daniel saying RAID 10 is super expensive. Yeah, and no, Jacob said no, he didn't get a job offer there. Yeah, so there's all different levels of RAID. They were obviously having a huge rack of them, so they were willing to spare the expense. And so there's various technologies, and we will definitely discuss some of the nuance, well, not nuances, but the basic concepts of RAID. You can see there it talks about hot spares, hot swap, and that's for to prevent failures of loss of data, and to be able to handle when a drive fails, that you have a backup recovery path. And it's basically shared storage utilized in a manner that produces better efficiency and redundancy. Features found in some file systems: snapshots, clones, thin provisioning, replication, and deduplication, etc., are directly related to that. I actually used a hard disk system from a company called NetApp, which I think is very common with some of these big disk farms. And it had the feature that I think it was half an hour or hour, a complete snapshot of everything on the disk was created. And it was really nice as a developer, because as a user, if you ever made a mistake, you could always go back to the snapshots and figure out what was on the disk an hour ago. So when you deleted a file by mistake, it wasn't as tragic, because you could actually go back and in most cases recover at least what was in the file an hour ago. You may not be able to recover what was in the file 5 minutes ago, but certainly what was in the file an hour ago or so. Other environments that of using disk is storage area network. So here it's a big network of storage arrays or storage servers, etc., and matching them up with clients in terms of access. This is great for shared storage from multiple users and multiple sites. So a storage area network is one or more storage arrays, like I said, connected to one or more fiber channel switches. So again, fiber channel is very fast, so that provides that. And then the hosts are attached to the switches and access the data and the storage arrays through to the switches. Storage is made available via LUN masking from specific arrays to specific servers, just sort of an implementation detail. Easy to add or remove storage, add new hosts and allocate storage, and you've added more storage. So again, it's very scalable, that you can scale it up or even down if you wanted to, but generally you're scaling up, of course. And it's over the low latency fiber channel fabric, which is basically means that the fiber channel is very, very fast. And so you don't suffer a large penalty with the network speeds. If you did it over, a slow Ethernet connection, over, conventional technology, you would pay the price in terms of disk access performance by the cost of the network. So you couldn't do it over a conventional network for the storage area network itself. And then here's also different other storage networks to consider, iSCSI and FOCO. Those are just different types. Network attached storage, or NAS, is storage made available over a network rather than over a local connection such as bus, remotely attaching to a file system. NFS and CIFS are common protocols. How many of you are familiar with NFS and CIFS? Okay, so NFS is Network File System. You generally see that in Sun computers, where Sun was toting that the network is the system. And so they're trying to emphasize interconnectivity of the network. And CIFS also is known as Samba, and it's common file sharing protocol in Windows and Linux systems that are interoperable, so that you can access files across the network on other people's systems. So it's basically tying on a disk via the network that can be accessed remotely as if it was part of your file system, but it is being accessed over the network. And just an implementation note that's just kind of, an aside, is that it uses remote procedure calls between the host and storage, typically over TCP or UDP on an IP network. So again, using standard TCP/IP networking, and then iSCSI protocol uses IP network to carry the SCSI protocol. So they actually have implemented the SCSI protocol over the network, and that's iSCSI. So those are the various networking technologies to expand the availability of disks across multiple hosts. So multiple computers can share the same disk storage. Moving on, we have disk scheduling. So there needs to be a way to schedule the requests to most efficiently be able to access the data that you're trying to access. The operating system is responsible for using the hardware as efficiently as possible to maximize the bandwidth and minimize the access time. in general, so we're talking about a hard disk drive here, magnetic hard disk drive. We're trying to minimize the seek time because again, the seek time is the dominant factor in the latency. And disk bandwidth is the total number of bytes transferred divided by the total number between the first request and the service. So that's just the mathematics of how you would calculate the bandwidth. There are many sources of disk I/O requests. The operating system could request something on the disk, system processes, and user processes. So basically, everything your computer does will typically potentially have hard disk requests that it's doing. So basically, the operating system's use has to keep in mind that there are all these different characteristics of processes that are going to request disk I/O. And you can imagine you may prioritize various types of processes. Access to the disk would be a potential thing you could do. So I/O requests include input or output mode. So you're either reading something from the disk or outputting it to the disk. You have to give it a disk address and a memory address. So this is where on the disk you're either pulling data from, reading it from, or writing it to. And then the memory address is where in memory is it being read to or written, So where is it being transferred to from the addresses of both ends? And then how much data? So the number of sectors to transfer. So the operating system will maintain a queue of requests, as you could imagine. And then idle disk can be immediately worked on I/O requests, which means that a busy disk means work must queue, so you have to wait. And so hence we try to come up with optimization algorithms that makes the most sense in terms of optimizing the available bandwidth of the hard disk because it is the slower component. And so you want to take advantage of every moment of time you can with the CPU. And then not the CPU, with the disk. But then remember we talked also in the overview about direct memory access, which takes the CPU out of the equation so that memory can be data can be transferred on and off the disk directly without the CPU would be involved. And we also talked about this with virtual memory, how that when you're doing free pools of logical frames or physical frames, that you can the pages and the frames that you can actually write and read to the disk in whenever there's free moments on the disk. You can take care of that so that if there is a page fault, that part of the operation can be done and the information stored in memory can be clean. Basically, it matches what's on the hard disk, and so that if it needs to be swapped out, you don't actually have to swap the information out to disk. So going through some algorithms, let's see. Going through some algorithms, we have first come, first serve, which very much sounds like FIFO, right? Like the FIFO when we talked about managing memory. So here we have the concepts are very similar. And so it's just basically whatever value comes in first, that's the one that gets accessed first. And that's first come first. So, make sure you understand this algorithm. So we can see here that it's at this particular sector. I don't know what it is. It's some big, large number here. And that the queue says 98, so it goes to 98. And then the next one is 183, so it jumps to 183. And then the next request is 37, goes to the next one, which is 37. So keep in mind, it's just straight. When it comes in, it's the next one in line. So understand that that's what the first come, first serve algorithm is. Another one is trying to optimize, because we know that the seek time is a significant factor. What we try to do is go to the one with the shortest seek time first, selecting the request with the minimum seek time from the current head position. So we can see here, it looks like it's 53 to 65 is the shortest distance. So it does that first, and then progressively goes through looking for the disk position that is closest in terms of seek time. So the shortest time first scheduling consists of form of SJF scheduling, which may cause some starvation of some requests. So remember we had in CPU scheduling, we had shortest job first scheduling. And so we know that similar to shortest job first in managing the CPU, that we can also have starvation in this case as well, the shortest time first. You can imagine maybe you would have a situation where you somehow promote the task that is starving and not getting access, and you escalate it somehow to move it up in the priority list. So the other station shows total head movement of 236 cylinders for this particular string of accesses of cylinders. So that's the shortest seek time first. Again, key thing here, it's the minimum time first. Very much like the charge job first, you look for the shortest one and try to take care of the short ones first. Another algorithm is the scan algorithm. And this takes advantage of that the disk arm is starting at is moving in one direction, and it takes time for the disk arm to slow down, stop, and go a different direction. It is far more efficient mechanically for it to keep going in the same direction. So in the scan algorithm, the disk starts at one end of the disk and moves towards the other end, servicing requests until it gets to the other end of the disk, where the head movement is reversed, and you service them going back the other way. The scan algorithm is sometimes called the elevator algorithm, where you're basically going floor by floor. Here you're going sector by sector, up and then down. And here, the illustration shows the total head movement of 236 cylinders in this particular one. But please note that if the requests are uniformly dense, large density at the other end of the disk, and those will wait the longest. So again, at the outer end of the disk, we know that the density is lower, and so the wait will be longer. Again, we have that uneven distribution of data on the hard disk. So the circular scan algorithm provides a more uniform wait time than scan because you have a large variability. And this is when the head moves from one end of the disk to the other, serving requests as it goes. However, when it reaches the other end, it immediately returns to the beginning of the disk and then comes back. So in other words, we're always reading in the same direction so that we get more uniform wait time, that you don't have one that's at the end and has to wait a long time. So it treats the cylinders as a circular list and wraps around from the last cylinder to the first one. The average wait time heavily dependent on the number of cylinders, right? Because obviously the number of cylinders will dictate how much the average wait time is. So again, this is another one of the algorithms. Make sure you understand these algorithms and what they represent. So the C-scan is we're always scanning in one direction. You go back to the beginning and then come back down again. So that takes us to the end of our time here. Does anyone have any questions before I dismiss you?
What's the difference between FIFO and first come first serve?
Oh, FIFO and first come first serve is pretty much the same thing. So in the disk technology, they use the term first come first serve. In page replacement, they use the term FIFO. They're essentially the same thing, right?
Okay, thank you.
Yeah. Any other questions? All right. Well, I look forward to meeting with you on Friday. And if you have any questions, feel free to stay after if you want to chat. So you're dismissed, and we'll reconvene on Friday.